Okay, good. So I'm going to briefly talk to you about a project that we've been doing with investigative journalists here in Le Monde, where we use graphs in order to find conflicts of interest in the biomedical domain. So first of all, what is a conflict of interest in order to get a bit into the point? So according to the French transparency law, a conflict of interest is any situation where a public interest may interfere with a public or private interest in such a way that the public interest may be or appear to be unduly influenced. So this is a definition, this is a law definition. In practical terms, if we discuss about the biomedical domain, and this is quite popular these days, suppose that now the EMA has to make some decisions about getting some vaccines. And then you want the people who make the decisions not receiving, for instance, funding from companies like Pfizer or AstraZeneca and so on and so forth. So the idea here is that we want to establish a database of conflicts of interest where it would be easy to find all the declared links of Dr. Alice with the company, say, HealthStar. So this information is usually available, but it is technically buried. And what we are doing is more or less what you see here in this figure. So we use PubMed database. We get bibliographic references, which are provided in XML format. So in there, we normally have conflicts of interest statements where the authors are declaring their conflicts of interest there. Or if this is not available, we also use the PDF files from where we extract information from the acknowledgements or from conflicts of interest statements there in order to find where some authors have received funding. And then we combine this information with other sources that are available online, for instance, provided by investigative journalists or other investigators like PharmaLeaks, where we can find the relationships that are between big pharmaceutical companies and other smaller unknown ones. For instance, that HealthStar is an NGO founded by pharmaceutical companies, blah, 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 as well as other open data sources. So in general, we take all these data which are heterogeneous, and we throw them, let's say, inside ConnectionLens, a system that we have built for where we use information extraction techniques in order to build a graph, store it in a relational database, and then we are extracting this graph from the relational database or the part of the graph that we want to search on. We load it inside the main memory in an optimized graph layout, and we query it using our query algorithm that I'm going to explain to you now. So before going to the algorithm, let's start with a few formalities. So what we want to do here is given a graph, which is built out of different data sets and some query keywords, we want to find the k highest score minimal answer trees, where an answer tree is a set of edges that form a tree together. And for each query keyword, they have at least one node whose label matches the keyword. And then we are even interested in minimal answer trees, which means that if we remove an edge from the tree, then we should lack at least one query keyword. And if we have a query keyword in the tree that matches the label of more than one nodes, then all those matching nodes must be considered equivalent. So our setting clearly is related to the group Steiner tree problem, but we further consider that edges are bidirectional since we do not have even any information on the direction of the edges from the sources that we extract them from. And in the end, we want to return the k highest scored trees among the ones that have been found during the search time. Now, the algorithm that we have for the search, we call it grow and aggressive merge, and I'm going to show you briefly how it works. We have, first of all, we find all the nodes that match the query keywords. Suppose the keywords are W1 to WM. And we start by those nodes. Say we start from node N1.2, and this is an answer tree which has a single root, which is this specific node. And then we explore the neighborhood of that node, and we decide to grow to one of those, which becomes, say, N2.2, 1, which becomes the root of the new tree. And we do this, of course, for all the nodes that are matching. We start from the matches, and then we start building the trees from there. And then you can assume, of course, that we may have several trees that have the same root. So when we detect trees that have the same root, we merge them together. Hence, they aggressively merge apart. So here you can see that we create a tree by merging the two previous answer trees. So one thing that we need to consider here is which tree to grow or to merge. And to do that, we assign priorities to the answer trees that result from grow and merge operations. And in general, we prefer the trees that match many query keywords so that we reach a result quickly. And if we have several trees that match the same query keywords, we prefer the ones of smaller size, since the users can see them and interpret them easier. So we implement this inside the priority queue, and every time, for instance, that we have an operation like the merge operation that we saw before, we throw that answer tree inside the priority queue. We apply the priority rules, and then we pop the next tree from the queue. We grow like we saw before, and then we recursively merge with all the same rooted answer trees. So clearly, as you can see, we have a mixed BFS-DFS approach of graph search. So when we grow, we go DFS, like we go deeper into the graph. When we merge, it's like going BFS, because we are expanding our trees. Inside the memory, the layout that we have inside the main memory is what you see here on this slide. So we have two main tables, the edge and the node. And these tables provide the main information that we need during the search. We also provide edge and node metadata, which are required, which include the information required for returning the results to the users. And finally, you can see here that we have a separate heap table, let's say, for keeping the node connections, because we want to have a constrained size for the node table. So we store here a k number of connections, and then the rest we store them separately so that we can have some static allocations. Finally, we have a keyword index so that we can have the starting queries. So that we know which nodes match which keywords, and here we support exact and prefix matching. Here we use a simple row major layout, which is CPU cache friendly for the type of queries that we run, since our bottlenecks is not that much the graph itself, rather than the intermediate results, as I'm going to explain to you in a while. One issue that we have here is duplicate work, and
unless you have 3 minutes.
Yep, absolutely. Okay, so here the idea is that since we don't know exactly where we're going, we are starting from different parts of the graph, and we are creating trees. Then we may end up looking at the same tree several times. For this reason, we maintain a history of the explored trees, and we examine an answer tree. We put it effectively in the priority queue only if it has not been explored before. So in order to do a parallel search, this becomes our bottleneck, because this history grows too large, as well as the priority queue, and this becomes the main bottleneck that we have. So in order to address that, we use, of course, several threads, and we follow, since we cannot partition the graph, because we cannot make any assumption on the shape, we use a shared everything architecture, and we rely on concurrent data structures, lock-free data structures, so that we can have several threads using them at the same time with minimal interference. And to just show you a bit of the queries that we've been doing, we have run some queries on 450K PubMed bibliographic notices from 2019 and 2020, 42K PDF articles, about 800 HTML pages. We have constructed the graph, loaded in the main memory, and run some queries with thresholds, either 1,000 solutions or 1 minute of execution time. This means that our query stops if we find 1,000 solutions or after 1 minute. Now, these are the results. Of course, we have anonymized them. On the top, you can see that the number of query, which keywords we use, time to the first solution, to the last solution, overall execution time, number of solutions, and number of data sources involved in the answer. Times are in milliseconds. So we use A for author, I for industry, H for hospital, P for country. And for instance, in the last query, we see that we have found connections between 2 authors and 3 companies. The time to find this solution took about 3.3 seconds, 28 seconds to the last solution, and we have mostly 11 data sources involved in those answer trees. So overall, ConnectionLens introduces an end-to-end pipeline for constructing and querying the graphs. We have migrated our graph in an in-memory engine, and we are querying them using our BigM algorithm. And these are the papers where you can find all the related information. These are of our proud funders. And that's it for me. Thank you very much.